Hello. So we're going to start a chapter on number theory. Okay, so this is going to start with divisibility and modular arithmetic. All right, so let's look at a definition of division. Okay, so we have a and b are integers, with a is not 0, so we can divide. And we say that a divides b if there's an integer c such that b equals to AC. Okay, so this is equivalent to saying that a b divided by a is an integer. When a divides b, we say that a is a factor or divisor of b, or that b is a multiple of a. Right? So we kind of know that just from arithmetic. Right? But we're going to introduce this notation with the vertical bar. So this notation right here, a vertical b, denotes that a divides b. And we say that a with the vertical bar with a slash between, this means that a does not divide b. Okay? So remember, a divides b if we can write b as a times an integer. All right? So let's look at these examples. So example A says, determine whether 4 divides 20. Okay? So this is yes. 4 divides 20 because I can write 20 as 4 times 5. It's 4 times an integer. Right. So does 20 divide 4? So the answer here is no, because I would need to have 4 is 20 times an integer, and this is not possible, right? Well, we know that 20 times 1 over 5 will give me 4, but this is not, 1 over 5 is not an integer. So this does not work. So 20 does not divide 4. Right, and finally, does 0 divide 5? And the answer to that is yes, because I can say that 5 is 0 times right, that doesn't work. So the answer is no, right? Because we were told that we want to have a not equal to 0, right? Because 5 is not going to equal to 0 times any integer. That's not possible. That basically, it's equivalent to division by 0, so this is not true. All right, so this is kind of our basic examples for this notation. A bar B means A divides B. Okay, so with this, we're going to build a few theorems of divisibility and modular arithmetic. Okay, let's look at our first theorem. Okay, we're doing this theorem in blue. Okay, so first theorem says that if a and b and c are integers where a is not equal to 0, then these three things are true. Okay, so the first one says that if a divides b, then a divides c, then a divides b plus c. Okay, so let's prove this theorem. And we're going to prove this with the direct proof. We're going to start with these are our premises, and this is our conclusion. So these are our premises, and we're trying to prove this conclusion. We're going to do this with the direct proof. So let's take our premises. So we know a divides b, and by the definition, we know that we can write b as a times an integer. And we also know that a divides c, so we can write c as a times an integer. Make sure to take different integers. If you take the same integer for both of these, then you're kind of looking at a special case rather than a general case. So we're going to say L and K are integers right here. All right, and then we're going to add these. Okay, so we're going to add them, and that's going to give me B plus C is AK plus AL, which gives me AK plus L. Now, K plus L is an integer itself. So because I can write B plus C is A times an integer, by the definition of what divides means, this means that A is going to divide into B plus C. Right? Sometimes you put the parentheses, sometimes not. Again, if you have the divide symbol, it implies that it divides into the whole expression here. But if you want to make it clear, do put a parentheses. That's helpful. All right, so let's look at number 2 now. Number 2, similar kind of proof. Number 2 says that if A divides B and A divides into BC, then A divides into BC for all integers C. Okay, so let's see how this works. All right, so let's get a color. So again, this is my premise, and I'm trying to prove this conclusion. Direct proof, again, is suitable here. So A divides B means that I can write B as A times some integer K. Is an integer. All right? And now we're going to multiply both sides by C. So multiply by C. If I multiply both sides by C, I'm going to get BC equals A times KC. Now because C is an integer, this right here is an integer. So I have BC is A times an integer. By the definition of divisibility, this means that A divides into BC. Okay, so that completes that proof there. All right, let's look at number 3. Okay, so number 3, I'm going to see if I can fit it into this space right here. Okay, so number 3 says if A divides B and B divides C, then A is going to divide C. Notice this is like a chain rule type thing, right? Again, these are my premises that leads into this conclusion. So let's start with the premises. So A divides B means that B can be written as A times an integer. As an integer. B divides C means that C can be written as B times another integer. Okay, and now we're going to substitute. We're going to take this and substitute it for B here. I'm going to say C equals AK gets substituted times L. I'm going to rewrite this as A times KL. We know this is an integer. So because C is A times an integer, then we say A divides into C. So that proved our conclusion. All right, so all of these are direct proofs. Just kind of showing some properties of divisibility. All right, so you can see this is like the sum rule, this is like a product rule, and this is like a chain rule type thing to see how like a number divides into other numbers, and the sum of them, the product of them, and sort of a chain rule type thing for 3. All right, we're ready for another theorem. So this next theorem, A, B, C are integer, A is not 0, such that A divides B and A divides C, then A is going to divide MB plus NC whenever M and N are integers. So notice this is like a combination of the number 1 and number 2 here. We're going to combine the sum and product, the scalar product theorem there. Okay, so we're going to start with our premises. So A divides B and A divides C. Okay, so this means that B can be written as A times an integer, and C can be written as A times another integer. All right. Okay. So now we're going to multiply both sides by m here. Okay, so we're going to take this and multiply by m. And we're going to get mb equals akm. We're going to take this and we're going to multiply this by n. So we're going to get nc equals a ln. Okay? Then we're going to add these. So we're going to add these two equations. We're going to get that mb plus nc is akm plus aln. Right? And we're going to factor out an a, km plus ln. So mb plus nc is a times this. All right, all we need to know about this is that's an integer. Okay, so because k and l and m and n are all given as integers, we multiply them, we add them together, the result is going to be an integer. So because a times an integer equals to mb plus nc, then by the definition of division, a is going to divide into, not into, a is going to divide mb plus nc. All right, good. So that proves this theorem right here. All right. Okay, so let's introduce some language, more language of division. So the division algorithm, it's called. Right, so we're going to introduce these terms right here. Okay, so if we divide, we have an integer a and a divisor d. Okay, so a is called a dividend and d is called the divisor. Okay, if you divide a by d, then you're going to get a quotient. Here's the quotient. And the quotient is denoted by this, a div d. Okay, so a div d gives you the whole part, the integer part of the division, right? And then we're going to define r, which is called the remainder. Okay, and this is called a mod d. So a mod d represents what the remainder of the division. So q is the quotient, is sort of the whole part integer of the division, and r is the remainder. Okay, so r is also between 0 and d. So it's a positive number. It could be 0. You could have a remainder 0, but it has to be less than the divisor. Okay, and then you can say that a equals the divisor times the quotient plus the remainder. Okay, so any integer a is formed by the sum. Okay, the divisor plus the quotient times the quotient plus a remainder. All right, so let's look at some examples. All right, so in part A here, we want to divide 101 by 11. We want to find 101 mod 11 and 101 div 11. Okay, so 101 div 11 is basically if you divide 101 by 11, the div gives you the whole integer. Okay, so how many times does 11 go into 101? It goes 9 times. Okay, so it goes 9 times. And if you do 9 times 11, you get 99. Okay, and then 101 mod 11 gives you the remainder. Okay, so it goes in 9 times. 9 times 11 is 99, but then you get a remainder of 2. Okay, so this mod function right here is really important in number theory. Number theory is very important with computers, especially with cryptography, all this sort of financial, internet security, anything that's sort of encrypted, like your passwords and all sorts of things, uses mod as part of the calculations to do all this encryption. So this is like hugely applicable and hugely important in today's how things work today. Okay. All right. So let's look at B. So we have negative 11 mod 3 and negative 11 div 3. So we're basically dividing negative 11 by 3. Okay. So with negative numbers, you want to make sure that your remainder is positive. Okay, so right here it says the remainder has to be bigger than or equal to 0 and less than the divisor. So you have, some choices like negative 11 divided by 3. You could say it's negative 3, and then you get negative 9, but then you get a negative remainder, which is not good. So the negative 3 is not a good choice. We're going to say that the divisor is negative 4. Okay, because now when I do this, I get negative 12. Right, so my remainder is going to be 1. Okay, so you want your remainder to be positive, right? So remember that we can write the number as this product sum right here. So you should be able to write negative 11 as your divisor times the quotient plus your remainder. Okay, so notice that this works because I have negative 12 plus 1, which gives you negative 11. Okay, so I didn't use the negative 3 here because that would have given me a remainder of negative 2, and you also always want your mod to be positive. That's kind of established by the definition. All right,